Very happy to have Mr. Rohit Singh as the speaker of our first session today. I take this opportunity to introduce Dr. Rohit Singh. Mr. Rohit Singh is a director of ISRI's AI Research and Development Labs in New Delhi, India. He's passionate about geospatial AI, machine learning, and deep learning, and bringing them to GIS. Rohit leads by example and empowers his team of talented data scientists, software developers, and product engineers to build the next generation of geospatial data science products. This awesome team is working on cutting-edge technologies and making groundbreaking advances in geospatial AI and next generation of enterprise GIS. Rohit possesses superior leadership, team building, communication, and interpersonal skills. He takes care deeply about API designs and has conceptualized, designed, and developed the ArcGIS API for Python and ArcGIS Engine Java API. He loves solving complex engineering problems, and his innovations underpin several product families in the Arcgis platform, including ArcObjects, Java, and Arcgis Enterprise for Linux platform. Rohit has worked at all levels of the software stack, from assembly code and device drivers to desktop applications, web applications to mobile and cloud technologies to deep learning. Conceptualizing software products and seeing them through to completion is a recurring theme in his life. He's a graduate from IIT Kharagpur and has worked at computer vision startups, TCS, and IBM before joining ISRI. He has been recognized as an industry distinguished lecturer for the IEEE Geoscience and Remote Sensing Society and serves as a plenary speaker at several international conferences. So it is a pleasure to hear from you, Mr. Rohit Singh. And we are really looking forward for this interesting talk on application of AI/ML for geospatial data and Earth observation systems. Over to you, Mr. Rohit.
Thank you, Dr. Suchet.
We are not able to hear you.
Can you tell me if you can see the screen?
Yeah, now you're it.
Okay, great. Well, thank you, everyone, and sorry for. Sorry, Dr. Suchet, were you saying something?
No, that's fine. Please go ahead.
I had a power. Had to like Dr. Suchet said, I'm Rohit Singh. I'm yes, Dr. Something. There's some WebEx setting. I'll just check my audio.
We are able to hear you, Rohit.
Okay. Then sorry, I wasn't sure. I heard you partially. So okay. Well, I hope it proceeds smoothly from now on. So I'm very excited to get this opportunity to be here and tell you about how now we at Esri are applying geospatial AI and deep learning to remote sensing and geographic data and some recent developments in this field. So some of the examples that I'll show are from Arcgis because of my industry affiliation, but they are quite generic and they would apply to GIS in general. So let's get started. Images, 6 beautiful images depicting different landscapes. You see a river here on the bottom left. You see an industrial city in Kuwait. On the right, there's a Permian Basin in Texas, where there are actually well paths. So what do you do with such imagery? How can you use this imagery? Well, you can use it for photo interpretation. You can use it as a base map or a backdrop in your geographic information system for context. But extract settlements are. You can identify new structures that have come up in this industrial city. You can growth, and you can do downstream analysis using this space-time cube to see how the drilling activity is progressing over time. And you can extract land cover. You can see the change in land cover. And just like in the movies, you can take blurred imagery and increase its resolution using super resolution techniques. And in this beautiful image from Sweden on the bottom right, there's a bunch of features like buildings that you can extract that can be used for infrastructure planning. Here's another example. This is in a suburban area of Texas. And over this region, you can see houses. Some of these have these blue swimming pools. You can see roads, the different kinds of land cover. And typically, it's hard to extract all this information. It requires digitization by a human to be able to get this information in a map. But all these layers of data that I'm clicking a button and they're coming up, like the swimming pools and the residential houses, now the parcels and the roads, they're all extracted using deep learning. So it's fully automated. So that gives you, uh, I hope, hopefully it'll get you excited enough about what's coming, what I'll be talking about. But first, let's have a quick overview of what I'll be covering in this session. So first, we'll go over a very short introduction to what is deep learning for those of you who are new to it and how it relates to geographic data, to GIS. And then we'll dive into geospatial deep learning. We'll talk about the different types of deep learning models for geospatial applications and see different examples of how they could be used. And then we'll see what's involved in a complete uh, workflow in which you could take your imagery, take such models or create such models yourself and extract information from them. And finally, we'll end with some uh, ideas of where new research is headed in geospatial deep learning and some resources for you to learn more. So with that, let's get started. So this whole session is about deep learning for remote sensing. So I won't make it long, but most of you already know that deep learning, which is a, a subtype or a kind of machine learning, it learns from data and it's loosely inspired by the human brain. There's a lot of layers of these neural networks that are able to find complex patterns and extract meaning from unstructured data. Now, in today's talk, I'll be focusing a lot on imagery, but you can do, apply these models to motion imagery or videos, or you can start tracking objects. You could apply it to point cloud or 3D meshes. And while today I won't go into a lot of detail about text and tabular data and time series data, you can actually apply deep learning to that kind of unstructured data as well and extract information and location from it. So why is deep learning important, and especially for remote sensing? As you know, there's a fire hose of imagery and data that's streaming down the pipe every day. Huge amounts of satellites, massive amounts of sensors and drones capturing high resolution and high temporal data, which is quickly becoming very hard to manage. So, and it's not just about management. The traditional approach to taking these images and extracting features from them doesn't scale anymore. Hence, we need to automate this process, and we can do that using deep learning, where we teach the machine to extract these features for us. AI, and in particular, deep learning is now the de facto solution for automating extraction of features from imagery. So let's see how we got here. On the right, you can see this chart that shows the error rate at recognizing what's in an image. These are results from the ImageNet Visual Recognition Challenge. And early on, it used to be machine learning that used to win that challenge in 2012 and used to have an error rate of about 25%. But since then, deep learning took over, and every year it kept getting better and better. And in the last few years, you can see how it actually became better that than humans at tasks like extracting, finding what's in an image. So we are getting lesser error from these models than what a human would have. So the moral of the story is that we as humans can no longer judge a machine that's better than us, and hence the challenge was stopped. And computer vision is now almost as good or even better uh, than human vision, at least in some imagery tasks. So what are those tasks, and how do they relate to geospatial deep learning? So let's have a look at the story map. A picture says 1,000 words. Let me just make it full screen. And here's a story map with several examples of what the different kinds of computer vision models are and how they can be applied to GIS and remote sensing. So perhaps the simplest one is object classification. So in the deep learning world, you show the computer a picture of a cat or a dog, and it assigns a label to that. Now, how can we use it for GIS tasks? Now, in this example, we've got these houses. Some of them are damaged due to a forest fire. And by feeding this into a neural network, an image classification network such as ResNet or Inception or VGG, you can have the machine classify these geographical features as damaged or undamaged. So a very simple application, but very commonly used in GIS. Next, another very important task is finding objects in and that's known as object detection. And in this map here, we can see how models like SSD, RetinaNet, YOLO, or faster RCNN can help you extract features, in this case, swimming pools, and draw a box around them. It's a very important task in GIS. Uh, Next, there's pixel classification that's known as semantic segmentation in the computer vision world, where we are assigning a class or a label to each pixel in that image. In GIS and remote sensing, it's used for land cover classification. So you can see where the different land cover types are. You can visualize change with temporal imagery. And you can do that. A very popular model is the UNet model, but there are newer models in that category that are available today. Another type of segmentation is instance segmentation. So we are not just finding the classes of each pixel, but rather we are finding masks of each object in the imagery. In this case, we use instance segmentation to help us do a better kind of object detection. So not only are we getting where these houses are in the form of a bounding box, but we are able to get their precise polygonal boundary by using instance segmentation models like mask RCNN being applied here for extracting building footprints. Then we've got models that are specialized for edge detection, like the BDCN or bidirectional cascade network, or the holistically nested uh, edge detection model. You can do that, use those to find edges. In this case, it's being used to find parcel boundaries. You could do it to find agricultural field boundaries. Then, especially for us in GIS, roads is a very important foundational layer, for routing, for example, and being able to extract roads using these deep learning models. And there are specialized models in, people working at the intersection of remote sensing and deep learning are creating these models. In this case, the multitask road extractor model. And there's also models called SAT to graph from MIT that can help you do things like extracting roads. Then there are models that work on a stack of images. And these are Siamese-based neural networks because they work on two images simultaneously and they can find the difference between them. So here you can see, as I'm sliding, we can see which are the new houses that have come up in this industrial town, shown in pink here. So you could use that for change detection. Another very interesting example is image generation or image to image translation. This uses generative deep learning, where you can use imagery from one domain and translate it into another domain. So here we are actually using the cycle GAN model to translate from SAR imagery to what it would look like in RGB or in optical. And it needn't just be for visualization. We've got another example that's able to go from Landsat imagery to the land surface temperature thematic raster. It could even be used for regression tasks. Then another very interesting application from the intersection of computer vision and natural language processing is image captioning. So you could have geographical features, and feeding that into the model, we can get captions that describe the image. In this case, it's saying that many planes are parked in an airport, just coming straight out of the neural network. This one is straight out of the movies. So you might have seen, CSI Miami, where they are able to zoom into low resolution imagery, and they like apply a magic wand to sharpen, but in reality, it's now possible to enhance the resolution of your imagery by training a model on that. And you can see how we can go from blurred imagery to much sharper imagery and increase its resolution. So that was a quick tour of the different kinds of models that are available, particularly for imagery, and how these computer vision models can be applied for GIS assessing tasks. Now let's look at how you actually do that. Like, what does the process look like? Or for those who are students or going into the industry, how does a GIS integrate these technologies? So I'll use an example in this from an ArcGIS Pro that I'm showing now. And here we are looking at Malibu in Southern California. Now this area was affected by a very devastating fire in the winter of 2018 called the Woolsey fires, one of the largest fires till then. And USAA, which is an insurance provider, needed to assess the buildings damaged by the fire so the claims could be processed quickly. And we worked with them on this project, and it's a huge task because there are 11,000 buildings, and the trained assessors need to go visit each building, see if it's damaged by the fire or not. But that's where we turn to deep learning. What we could do is deep learning, as I said, is a data-driven technique. It's a kind of machine learning. So we feed the model training data. We show it several examples of what damaged and undamaged buildings look like. But we only need to do it for a fraction of that data. So we've done that for about 1,000 buildings of those 11,000. And we label these buildings. So you can see the buildings that are damaged are shown in the red color here, symbolized using that color. And the buildings that are still standing are shown in the green color. And ArcGIS has tools that let you label this imagery, assign the proper attribute. Now, using this as training data, we can use tools available in ArcGIS and Image Analyst to export this data to image chips so that we can train the model. Now, these image chips, well, my Explorer just froze up, but they are small tiles, and we'll have a look at them shortly anyway in another example. They're small tiles that are able to fit into the GPU memory so that the neural network can be trained on it. And once we've trained the model, once we've exported those chips, there are additionally tools that let you train the deep learning model as well. So you just point it at the training data. It looks at those image chips. You can specify how many iterations it should look at the data to optimize itself. And you can pick one of dozens of different kinds of models that I showed you. All of the models that I showed you are actually available in ArcGIS. And you can train these models using a click button interface. And finally, you can even use the trained model, which is basically just a file containing the weights of the trained neural network. You can use them with these inferencing tools to classify objects. And in this case, yeah, that's what we wanted to do, to classify them as damaged or not. So here are the results. By applying that trained model, we're able to classify all the buildings in that area as damaged or not. So this really helps speed up that process. Now it's possible that, and here are some examples from the results. So you can see how well the model is actually, it gave an accuracy of over 98%, which is approaching the accuracy of a trained assessor. But it's possible that you might not have building footprints in some areas, like there's newer development or there's missing data, like in this case. So can we use the building footprints that we saw earlier? That's also data. Can we use that to train another model to find out what those building footprints are? Sure. Using the similar technique to train, export that data in the form of classified tiles, we are able to train a model. And in this case, I'll use Jupyter Notebook, which many people in the deep learning world use Python. And here I've taken that training data containing building footprints overlaid on the imagery shown in pink. The building footprints are shown in pink. This is what the training data looks like. And then we can train, again, one of those pixel classification or the semantic segmentation models like UNet, feed the data into the model, find a good learning rate. There are tools for that, and fit the model to the data. Once you do that, you can visualize the results of the model. The left column shows the input imagery and the ground truth building footprints. The right one shows the results from the model, the predictions. You can see how it's doing a great job at finding these buildings with the trained model. In fact, in this example, this building, these two buildings were missing in the training data or whatever the human label data is, but the model is able to extract them. So this is a pixel classification model, and let's have a close look at what the results look like. So let's go to a building footprint example. Now, because it's a pixel classification model, it's classifying each pixel as being a building or not. But we need something better than that. We want the boundary of these buildings or their footprints. And you can see how it's not very clean either. So that's where the post-processing tools in ArcGIS come in handy to clean up that raster. And we've got specialized tools to regularize or orthogonalize the buildings so they have right angles and straight edges. And with that, we can get beautiful building footprints from the deep neural network. I'm surprised that deep learning is really, how well it's able to do this task of extracting building footprints. So let me switch back to the slides. What we just saw was this workflow. I was able to do the labeling in ArcGIS Pro, export that data, feed it into the model. I showed you two ways in which it could be done using tools and notebooks. And then I was able to do the inferencing to get my results. But the real value is when it gets combined in a GIS with image management and analysis tools. And that's what ArcGIS lets you do. It's a complete end-to-end geospatial deep learning system. So as users or someone who wants to apply these, how can you use these? Well, you could use these tools in ArcGIS Pro, which is our desktop application. But you can also use it in ArcGIS Online, which is our web-based GIS, and ArcGIS Enterprise, which is for on-premises hosting by organizations. You could use these models inside of Jupyter notebooks, which run within Pro or within ArcGIS Online, or straight vanilla Jupyter notebook. So there are two ways in which you as users can apply deep learning and get started. You can start off with pre-trained models that Esri provides. You don't need to train your models from scratch, especially for foundational GIS data like building footprints or roads or land cover. We have done the effort to train these models and created a number of over 30 pre-trained models that you can just apply on your imagery. So this eliminates imagery requirements for training your data. It eliminates the training samples that you need. Our models, for example, the building footprint model was trained on millions of actual polygonal building footprints. And then training these models takes compute resources. So you can save on that as well. And those three steps that you saw of labeling, data prep, and training can be just replaced with these pre-trained models. You can go straight from the model and do the inferencing. So on ArcGIS Living Atlas of the world, we have released about 30 deep learning models. We are releasing more every month, and they can do a variety of things, like their models for land cover classification. And you can see some examples. It's again better seen through a demo. So let me show you another story map that goes through these pre-trained AI models. So for feature extraction workflows, one of our most popular model is the building footprint extraction model. And we've got it for 3 geographies now, United States, Australia, and Africa. Here's a model to detect swimming pools in imagery. Then we've got models that work with drone imagery, such as this one to detect cars and solar panels. And we are shortly going to release another model for solar photovoltaic fields. This one works on bathymetric data to detect shipwrecks. And these models also work with SAR data. This one is able to detect ships on SAR data, so can be used for seeing the maritime operations or defense. Then for land cover classification, we've got models which we've pre-trained that work on Sentinel and Landsat 8 imagery. Human footprint, is another important use case. We've got specialized models for that can find where the human settlements are. And then it's not just for imagery, even for 3D data like point cloud. We've got pre-trained models that let you extract these power lines or trees. We've got models that help you with redacting faces and license plates, and also models that work on motion imagery. In this case, this is using the CMask model to track objects in motion imagery, full motion video. So let's have a quick look at the website where you can find these models. I'll just go to the Living Atlas. I have that browser, Yes, let me just get it here and load it. So that's ArcGIS Living Atlas of the world. Not only can you find deep learning models, you can find a lot of foundational GIS data like layers and imagery, feature data. And in this case, I'm searching for deep learning package. And all of these are available to all ArcGIS users. They can be used with ArcGIS Pro or web-based offerings. So just going through a few of these models. and they're coming out every month. This is the power line classification model, the object tracking model that you saw. Uh, the palm tree. One of our most popular models now is the one to extract roads, and that works globally. It's based on MIT's SAC2Graph model. Now let me switch back to the slides and let's keep carrying on. And now let's see, how we can use these models to create foundational GIS data. So here is imagery from the country of Grenada that has provided us this data. It's a country in the Pacific island, and it receives over 70 of rain every year. It's susceptible to flooding and rather 70 centimeters of rain. And in the red, you can find the flood susceptibility map. So we want to see how many buildings are affected by these floods. Now, unfortunately, the country does not have that layer of building footprints, but we can use the imagery, and you can use these pre-trained models that are available on the web as well. And in this case, we chose the building footprint extraction model. And in the interest of time for this demo, I've already run it. And here are the results of the model. In the city, there are over 55,000 buildings that the model found. And by doing overlay analysis, we found the 1,500 that are in the flood prone area. Yeah. Similarly, by using the road extraction model, we are able to find roads. And by getting this foundational GIS data into a 3D scene and applying our point cloud classification models, we were able to create a digital twin of the entire country, complete with power lines and trees as well, that you can see here. So that's using the pre-trained models. But what if you've got features of your own interest that we don't have models for? Or what if you want to do it in a geography that we've not provided the model for? Mind you, buildings in India are different from buildings in the United States. So you cannot expect the same model to work here as well. So you've got choices. You can train your own models as well. And these models are especially useful for specific geographies, resolution, your type of imagery, and the specific asset types that you have. And again, you have two choices. Some people like to, analysts like to use tools. So we are building tools that you can, users can click both on the desktop application as well as web application. And then a lot of data scientists like to use Python. So we've got our own library called Arcgis.learn, inspired by scikit-learn. And just like scikit-learn makes it very easy to train good quality models for machine learning, Arcgis-learn lets you do the same for geospatial deep learning. And it's got, again, over 30, in fact, now more than 50 models on a different variety of tasks that you can train these models on. And then looking at the tools, here are some examples of these tools. They are not just for imagery that we saw, but we also have tools that are able to georeference motion imagery. You can see on the right here, as the truck is being tracked, we are drawing its path on the map as well. And there are models that work with 3D data. In this bottom example, it's used to extract railway lines, and on the top, it's used to extract power lines for vegetation encroachment analysis on 3D data. So let's have, for those of you who like to use Python, let's see how you can use the Arcgis Learn library and what it gives you. And here I'll be training a model from scratch on a limited amount of data just to show you how easy it is to train these models. And this is a land cover classification model. So we'll be using this data from Chesapeake Conservancy. that has, in 2013, they labeled a lot of data. We've gotten that in ArcGIS Pro. Here's the imagery, and here is the ground truth labels obtained from Chesapeake Conservancy. And to train the model, we'll be exporting that data out as chips. And this is what those chips look like, those image chips or tiles. This is the imagery. And these are the classified land cover labels that the model will learn from this training data. So to train the model, you can of course use the deep learning tools. But as a Pythonist, I like to use Jupyter notebooks for my work. And here I'll be training a model from scratch on that data by importing the UNet classifier from arcgis.learn. So this is a very simple library. You just point it at the data. Here I'm pointing at the exported image chips and the labels, the folder containing those, and specifying a batch size based on how big my GPU is. And we can visualize one batch of that data. This is what it looks like. The land cover has been overlaid with a transparency on top of the image chips. And basically we feed that data into the model, and we can simply train it. But before we train it, I'm calling show results to see what does an untrained model do. And you can see the left and the right columns containing the ground truth and the predictions don't match at all. This is because the model is not trained. It's just random weights and biases in that model. So to train the model, all you need to do is call fit. You can provide a learning rate. If you do not, we have techniques to find an optimum learning rate. And we've really made it very simple. It uses a lot of intelligent defaults and recent developments in deep learning to figure those out. And we are training it for 10 epochs or training passes over that data. So as you can see in the fourth column, with each epoch, the accuracy of the model is going up. And since it's only like a handful of image chips that I'm training the model on, to be able to do it quickly, it's only taking less than a minute to train this model. And once I've trained the model, again, I can call show results to see how well this trained model does. Now, mind you, it's not trained on huge volumes of data, but you can see how in under a minute, I was able to get a model that's able to identify the major land cover classes correctly. Now, training a better model is all about giving it a lot more training data and training it for a lot longer. And here you can see the results from such a model that's trained on that entire data. Once you're satisfied, you can save it out as S3 model definition. And here I'm applying that model type pass model and specifying this small extent so we can do it quickly. And since I have a GPU, I am choosing that. It's much faster using a GPU. And here are the results. So this is the imagery. And what we are looking at now is the ground truth data from 2013 when that row of houses wasn't there. But with the trained model, we can see how that row of houses that was missing is now available or is detected by the model. So you don't need to invest that time to label all that data once again with a trained model like this. Additionally, another benefit of the pre-trained models is that you can take those models and fine tune them to a newer geography. So there's an example that one of my colleagues did recently, and that was to identify the refugee camps that have tents, and they are, the USA building footprint model didn't do a great job at identifying those, but with a very little training data, he was able to train, or rather fine tune, the Africa building footprint model, not the USA model, on this geography, and it's able to do a great job at identifying these tents. So we can do downstream analysis, such as finding, how many residents have sanitation facilities, for example. So what's special about, the Arcgis Learn module? Well, for one, it makes it very simple to train these dozens of models in a very few lines of code. And that's a trend you'll find across the industry. First there was TensorFlow, then came Keras, which makes it simpler. And in the PyTorch world, starting with PyTorch, then FastAI or Lightning, and now with ArcGIS Learn, not only can you train a variety of these specialized geospatial deep learning models in about 6 lines of code, you can do that for dozens of models across various tasks using a very similar interface. Now let's look at where this is headed. Some examples of the research where it's going for deep learning, in particular geospatial deep learning. So here we are looking at the API for ArcGIS Learn. It's a Python API. And we've got on the left column, we've got models for different kinds of imagery and non-imagery tasks as well. So you've got models for object classification and detection, image translation, even video or 3D. But as you know, deep learning today is a very data hungry thing. It needs to be trained on huge volumes of data. And one of the recent trends or research, active areas of research is few shot learning. How do you train good models with a very limited data? And once you've trained the model, how do you extract the most out of such models? So here's an example of some upcoming models that we are adding to the API. And this is using DetReg, which is based on the Detter transformer-based architecture. So it's no longer convnets. Now the transformers are coming to computer vision. And once again, you can simply train this model. This is based on very recent research, a 2021 paper by Amir Bar. And we'll be training this model on just a few image chips. I think less than 50 chips is what we use for here. Once again, there's a different kind of model, but the same training methodology. Create the data object, create the model, fit it to the data, save it out. And this is to detect these palm trees. So looking at the results, you can see how well the model is doing. And then again, we are going back to ArcGIS Pro. And here we are using the detect objects tool to find where these palm trees are and running that model on this imagery. And here are the results. So with a model that's just trained on 50 labels, you can see how it's able to do a great job at finding a lot more of these trees. But there are still a few trees that it left out. And that's where another upcoming capability comes in, which is to use data augmentation, not just while training the model, but even while inferencing. So basically, it's known as test time augmentation, in which we feed not just that image, but flipped and rotated versions of the image and give it multiple chances to train their model, to do the inferencing. Well, all users need to do is turn on test time augmentation to true and run the same model. And then here are the results from that model. And you can see how it's able to find even those missing trees. So improving models so they can be trained on less amount of data using few shot learning. That's a research direction that we are taking, very active area of research today. And then getting the most out of your models. using techniques like test time augmentation. Now I'll show you some examples from the 3D research that we are doing. And we are doing it in two areas. One is for content extraction. So from point cloud or photogrammetric meshes or RGB and depth rasters, we want to extract the 3D building shells. So this is, to create these digital twins. And then we also want to do content generation for simulations, for example, creating entire 3D buildings and a whole city using generative deep learning. So let's see some examples of that. So here you can see example of taking a photogrammetric mesh and segmenting it into the building and the non-building class. So you can now start clicking on a building in a mesh, and only that, you can start attaching attributes to it, for example. And here are results from the mesh CNN model that we applied on it. Here's another scene. So you can see we are again doing mesh segmentation. And here we are seeing the results in the form of point cloud. So doing that for the point cloud. Now this is about generating 3D buildings from 2D data. So from an image, an RGB image, and a depth raster, the normalized DSM, we're able to extract 3D building shells. And this is using a recent paper called Mesh RCNN in the faster RCNN family. So the advantage of doing it like this is that we are able to get rid of artifacts from the photogrammetric technique, and we can extract noise-free buildings. And here's an example of virtual scene generation from a land cover map. So we feed in a land cover map using Pix2Pix and Pix2Pix HD. We can generate simulated elevation rasters and the generated RGB imagery. This is just imaginary scene created or conditional upon the input land use polygons and the roads that we fed into the model. And similarly, using Pix2Pix HD, we're able to generate the facades and the texture map to be applied to those buildings. And finally, combine these different models to arrive at urban scenes that have been generated by deep learning like this. Now, this is still very active research, so these models are not perfect, but I wanted to give you a glimpse into the kind of work that we are doing at Esri in applying geospatial deep learning and using it for remote sensing and GIS. For those of you who want to learn more, I have shared some resources on the slide here. So if you want to take a screenshot, you can do that here. Most of the examples that I showed you can be found as sample notebooks at the developer website for our Python API. And then another recommended resource, our Medium GeoAI blog, where we've spoken about the research in particular in a lot more detail. And for those who are new to deep learning and want to get started with it, I highly recommend the Fast AI course. That's how I got started with deep learning coming from the GIS world, and I highly recommend that. So that's all I had, and I want to thank you for your time. I'm sorry, I'm close. I still got done in time, but we only have like 5 minutes. If there's time for questions, I'll be happy to take those. Thank you.
Thank you very much, Dr. Rohit. We have a few questions in chat. The first one is from Filsa Finmanis. He is asking whether when using Arcgis.learn within Arcgis Pro, are you using your own PC's resources or from Arcgis Cloud?
Oh, okay. Well, Arcgis.learn is a Python library that uses the resources on the local computer. That said, so it'll be if you run it, you can download it. It's a Conda package. You can download it and install it on your system. And I do my deep learning on my laptop, which has a GPU. But if you like to use the cloud GPU, we've got ArcGIS online notebooks, and they also come with GPUs. So we have a cloud offering, and in those notebooks, ArcGIS Learn is pre-installed along with the dependencies, so you don't need to manage them yourselves. So we do have options for that.
Another one is comment from Costas Vlachos, saying interesting and useful presentation.
Thank you so much. I'm glad you liked it.
Yeah, and his query is that is ArcGIS.learn standalone this thing a free Python library?
So it is. It is a Conda package that anyone can download and install, but it does work with ArcGIS. So you need either ArcGIS Pro or ArcGIS Online to be able to use it, because the inferencing engines and the training data comes from there.
There are another two questions. Rohit, can we take them?
Sure, absolutely.
Yeah, the another question is when will YV4 become available in ArcGIS Pro?
Sorry, I missed the question. What will become available?
It's YV4.
YV4. I'm not sure if
So,
maybe I don't know about what YV4 is. I'll try to look it up in the chat if I'm missing the spelling.
yeah.
Okay.
Sir, good evening, sir.
Yes.
Can you hear me?
Yeah.
Yeah.
Yes.
Okay.
Oh, you mean YOLO V4? Okay.
Yeah.
Okay, got it. Okay. Okay. I see. Well, YOLO V4 is old now because we've got YOLO V5 and there's another variant. But that said, what we've done is we've integrated, we'll never be able to keep pace with the research that's going on. Deep learning is such a rapidly progressing field that every month there are new models. So one, I think what great thing we've done is we've integrated with detection and segmentation. And these are open source libraries and frameworks into which all the new models are getting integrated. So using that as a bridge, you can use the latest models for object detection and segmentation. And using TIM, which is PyTorch imagery models, the TIM library, we can get access to hundreds of image classification models in ArcGIS Learn.
One question is from Mohammad Iqbal. He wants to know that could we integrate ArcGIS and Jupyter Notebook from Anaconda to call the ArcGIS library? And if possible, what library should be installed?
Yes, so the library is actually called ArcGIS, and let me quickly show you the developer site. That's the ArcGIS API for Python. That's what you need to install. There's a guide that talks about how to install the API, and you can use it with Anaconda and Jupyter Notebook by getting it from there. And then additionally for ArcGIS Learn, we've got another meta package called ArcGIS_Learn, and that lets you get all the dependencies in order. So it's built on top of PyTorch and FastAI and Hugging Face transformers. So that helps you manage all the dependencies, that ArcGIS Learn meta package.
Khadija wants to know that does pixel classification refer to semantic segmentation?
Yes, exactly. What we call as pixel classification in GIS and remote sensing, we're actually using the semantic segmentation models like UNet or PSPNet or DeepLab for those tasks. There are three kinds of segmentation. There's semantic segmentation. There's also instance segmentation that I spoke about. And we use that for an object data, such as finding the precise polygonal boundaries of, say, building footprints. And now there's this newer kind of model called panoptic segmentation, or rather the task, that lets you segment a scene into stuff and things, and stuff ends up as classes, the pixel classes in ArcGIS, and things ends up as features, geographical features with polygonal boundaries. And that's another called Max Deep Lab that we are integrating with ArcGIS Learn coming up shortly. In fact, we just released it actually about a month ago.
Abhishek wants to know that can ArcGIS Pro available for free for researchers?
I do know that ArcGIS Pro has a trial license available. There are also, depending on your geography, it is available to different extents. So you should contact your local S3 distributor to find out to what extent it's available. But across the world, it is available as a trial license. And in some geographies, even I believe it's some universities already included. And for K12, K12, it's available for free as well. It depends on where you are and your university and things like that.
Yeah, and there are many comments expressing the gratitude for the excellent and informative presentation.
Well, thank you so much. I mean, my Saturday was had a little more energy because of this. So thank you for giving me the opportunity. And I'm sorry I got a little late, but I'm glad we are able to finish just in time. So thank you so much.
So since I do not see more questions in chat, we would like to thank our today's speaker, Rohit Singh, for the excellent and informative session. And Rohit, can I also ask you one question, or rather a query?
Sure.
Yeah, I'm working
Absolutely.
of AI/ML applied to planetary data, particularly lunar data. So I was really wondering when you were telling about the pre-trained models available, pre-trained data available. So I was really wondering that whether ArcGIS will be providing such pre-trained data and models for lunar data also.
Well, you just need to ask and we shall deliver. In fact, I'm just joking, but we do have a sample notebook that I can point you in the chat. That is, we've already created that, and that lets you detect lunar craters using deep learning. So if I could, I don't know, can you still see my screen here?
No, screen.
Or did I, I stopped sharing. Yeah. But anyway, I'll post it in the chat so everyone can see. And that's a sample notebook on our GitHub repository that shows how lunar craters can be detected using deep learning. It's a complete flow that we tried out, and yeah, you could give it a shot.
That would be great. Really, this is my precise area of research. Thank you so much.
Awesome. In fact, there's a new challenge, and it's called the Martian Craters Detection Challenge. That's coming up. I recently became aware of it. So you could, it's not just moon anymore.
Yeah. Okay. Thank you so much, Rohit. And
All right.
as we all are working in the online mode. So the memento giving thing would also we would like to present in the online mode. So I would request Tejal to present the online memento to Mr. Rohit as a mark of appreciation.
Awesome.
Thank you so much, Rohit.
Thank you. Absolutely loved it. And thank you and have a great day. Bye-bye.
Sir, can we have one group photo with the participant?
And I would all to just put on your
to.
cameras.
And I'm so thankful, there's great presence, a lot of people. I'm really excited and pumped after delivering this talk. So yeah, please everyone turn on your cameras. Let's have a group photo. It's so great to see all of you. I mean, this is what we miss in these, virtual mode. But
Yes.
it takes a little bit of effort, but it really helps give the human touch, especially in these virtual settings.
Smile, everybody. Thank you.
Thank you, and have a good day.
So we would like to welcome Professor Mihai Datku, and he's the second speaker for this session today. And I would just like to introduce Dr. Mihai to the session. Dr. Mihai Datku is from German Aerospace Research Establishment, TLR, Germany. And the title for his talk today would be Physics-Guided AI, Hybrid Paradigms and Quantum Machine Learning for Earth Observation. Mihai Datku received the MS and PhD degree in Electronics and Telecommunications from the University Politehnica from Bucharest, UPB, Romania in 1978 and 1986 respectively, and the habilitation of de rigueur des recherches degree in computer science from Université Louis Pasteur, Strasbourg, France in 1999. Since 1981, he has been a professor within the Department of Applied Electronics and Information Engineering, Faculty of Electronics, Telecommunications and Information Technology, UPB. Since 1993, he has been a scientist with the German Aerospace Center, DLR, Wesseling, Germany. His research interests include explainable and physics-aware AI, smart radar sensors design, and quantum machine learning with applications in Earth observations. He has held visiting professor appointments with the University of Oviedo, Spain, the University Louis Pasteur International Space University, both in Strasbourg, France, University of Siegen, Germany, University of Innsbruck, Australia, University of Alcalá, Spain, etc. From 1992 to 2002, he had an invited professor assignment with the Swiss Federal Institute of Technology, Zurich, Switzerland. Since 2001, he had been initiating and leading the Competence Center on Information Extraction and Image Understanding for Earth Observation, Paris Institute of Technology, France, a collaboration of DLR with the French Space Agency, CNES. He has been a professor holder of the DLR CNES chair at Paris Tech. He has initiated the European framework projects for image information mining and is involved in research programs for information extraction, data mining, and knowledge discovery, and data science with European Space Agency, NASA, and in a variety of national and European projects. He is the director of Research Center for Special Information, UPB. He is a senior scientist and the Data Intelligence and Knowledge Discovery Research Group leader with the Remote Sensing Technology Institute, DLR, and delegate in DLR ONERA Joint Virtual Center for AI in Aerospace. He is member of ECA Working Group, Big Data from Space, and visiting professor with ESA's lab. He was a recipient of National Order of Merit with the rank of Knight for outstanding international research results awarded by the President of Romania in 2008 and the Romanian Academic Prize Tran VUA for the development of SATI image analysis system and his activity in image processing. In 1987, he was awarded the Chardy Excellence International Blaise Pascal for international recognition in the field of data science and Earth observation. He has served as a co-organizer for international conferences and workshops and as guest editor for special issues on AI and big data of the IEEE and other journals. He is representative of Romania in the ESA Earth Observation Program Award, EOPB. He is a renowned IEEE fellow. We are really glad to have him as today's speaker and looking very much forward to your talk.
Thank you. Thank you very much for inviting me to this school. I am very happy to be here. So I would like to start the presentation. I'm sharing the screen.
Yeah, Dr. Mihai, we are able to see your screen.
Not yet. I apologize. I think I did
We are
something.
able to see. We are able to see.
Just a second. Is now visible?
Yes, please.
Yes. So the topic of today is physics-guided artificial intelligence, and it's presenting hybrid paradigms and quantum machine learning for Earth observation. I would like to start with an acknowledgement to my colleagues in my team at DLR on data intelligence and knowledge discovery, at Munich Aerospace, a cooperation of Technical University Munich and DLR, at the International Chair of Excellence, Blaise Pascal, in France, in Paris, and my team at the Research Center for Spatial Information, Geospace Tech, at University Politehnica in Bucharest. I would like to start the presentation with a short movie, which is presenting actually the main objectives and challenges of information extraction and valorization of big data from Earth observation. This very short 1 minute movie is part of a movie which was broadcasted on the German national television ARD and the French-German television Arte. I would like to acknowledge Professor Peter Baumann, who organized this project. So I will start the presentation of the movie, letting the original sound.
Information being lost because data is being collected that can never be analyzed. The German satellite data archive near Munich contains vast amounts of valuable data collected over the past 30 years. The archive can store more than 50 petabytes of data on magnetic cassette tapes. It may be that these tapes hold the answers to questions that won't be posed until sometime in the future. But when that day comes, will we be able to access the data? The more data we save for later, the greater the risk of losing information forever. Even the best storage media can age and become obsolete. But maybe there's a way to master the deluge of archived images and virtual reality. Researchers are mining the satellite data archive, hoping to make its information more readily accessible. As if the archive were a library with open books lying before them, the scientists can pick out an image, dive into it as it were, and check to see whether it shows structures similar to those on other images. The computer works like an automatic sorting facility. It searches the images for components like vegetation, farmland, bridges, and water. The computer sorts the images into stacks and categorizes them by their content.
At the present, they probably store in archives more than 10 to 20 million of satellite images acquired after the 80s. With a new era of the Sentinel satellites of the European Space Agency, the data volume per day will reach the level of 10 terabytes as their data rate. So we are going to reach soon thousands of petabytes of data, which is a large volume of data, and all the research community is putting huge efforts in dealing with information extraction.
Soon, we will no longer be talking about millions or billions of images, but trillions. And then it will be more important than ever to uncover meaningful information hidden in the mountains of data.
So I will continue
Information.
the presentation with the first page of the seminal work for Claude Shannon in 1948, a mathematical theory of communication. So in his paper, Shannon mentions that we deal with effective noise, with statistical structure of the original message as a final destination of information. And he mentioned very early, frequently the messages have meaning. They refer or are correlating according to some system to certain physical or conceptual entity. At the time he noticed the semantic aspect are irrelevant. That is not anymore true. Today, everything in communication, in information transmission, is about semantics and physical and conceptual entities. So I start this example with a multispectral image of Sentinel-2, the Copernicus European Space Agency satellite. These are the RGB channels visible. The infrared channel of the same sensor is different. The cloud disappeared, but we still have the shadow of the cloud. While infrared is sensing closer temperature, we have a physical measurement, a physical sensor, and it's extracting a conceptual entity and also semantic, because we have a description of the sea, lakes, urban areas, rivers, clouds, and agriculture parcels. We go to a more complex sensor, and a very important one, synthetic aperture radar. Why is synthetic aperture radar so important? Synthetic aperture radar is very important because it's an active sensor. It's independent of the sun illumination, and because of the long wavelength centimeters, it's penetrating the clouds. This means makes possible observation independently of day and night and weather conditions. And that is very important for very large areas of the Earth. However, synthetic aperture radar is much beyond visual system. So if we have this synthetic aperture radar image, we need a lot of imagination or knowledge to invert and be able to draw the landscape, which is a lake, mountains, and glaciers. Synthetic aperture radar are actually modulations of the microwaves in amplitude, phase, and frequency. And these contain complicated high complexity signatures which need to be inverted. So for such complex signals to extract information and understand such a building. So these are actually reflecting now in the artificial intelligence methods, which are disconnecting and evolving in a direction of physics-aware methods, which is different from the most general and known computer vision. And these are, in the beginning, two simple examples. We have a multispectral image of certain bands from which we visualize RGB. That's our perceptual capacity. And in this image, we have these three areas which apparently they look different. In this image, we have three areas, the one marked, which apparently look to be similar. However, this decision of difference or similarity is based looking only on three spectral bands from certain bands. In reality, if we apply deep learning, like sensing the information from the sensor, we transform this in a pseudo color. It's a kind of microscope which is extracting the basic information from our multispectral data. And in here, we notice that actually these three areas are in reality similar. And these, which are similar visually, they are in reality dissimilar. Why? Decision based on three bands is different from decision taking information in certain bands. The same happens with deep learning and artificial intelligence from synthetic aperture radar. Synthetic aperture radar are doppelgangers, are not images of the objects, they are images of the scattering of the microwave on the object. And that's an example of a gun which is learning not the image, is learning how the scattering takes. And from this we generated artificial images based on the scattering model of the TerraSAT-X, a German satellite image. So these results have been published recently in IEEE JSTAR. And these results are enhanced. We are able now to extract information from certain bands, use the infrared capacity to penetrate clouds and haziness, and extract recovered information from atmospheric effect or smoke in case of burned areas, forest fires, which unfortunately have been very frequent in the last time, and obtain from the certain bands a synthesis in 3 bands, which makes evidence of all the details of the land cover going through the atmosphere or smoke. These aspects are actually formalized in 2 concepts, the sensory gap and the semantic gap. So sensory gap is actually the difference in between our visual perception and the sensor range of measurements, as we already presented in infrared or in synthetic aperture radar. The semantic gap is actually the hope for our algorithms to extract the true semantic. So in a situation, we have a sensor which is observing an area of vegetation. Based on the physical parameter, we extract vegetation. However, a human observer in the context of a urban area decides it is a park. So there is a difference in semantic between vegetation and park. And these aspects, both semantic and sensory gap, are very important, and they have become a key issue in the Earth observation. And that's an example of implementing a Bayesian generative model latent hierarchical allocation for a parametric synthetic aperture radar, extracting a bag of words of basic signatures and obtaining semantic rules and semantic classes. So in addition to semantic classes like forest, urban, agriculture, or bare land, we obtain the explanation. So woody vegetation is explained by 53 multiple scattering, 34% of volume scattering, 30% of surface scattering. So that's an example of a problematic we have now in Earth observation to deal with these aspects. Artificial intelligence, and particularly deep learning, are methods which are relying a lot on the training data sets. So data is as important as the algorithms. Many times, the same algorithms trained on different data sets will behave very, very different. And in Earth observation, we have a challenge compared with computer vision. In computer vision today, we have benchmarks and training data sets of tens of millions labeled pictures. This is obtained mainly by crowdsourcing. In Earth observation, we do not have crowdsourcing. In Earth observation, we have a multitude of sensors. Compared with computer vision, we have a camera photography. So we have a synthetic aperture radar, we have time series, elevation model, polarimetric data. And that is raising the challenge on how to design tools and procedures to generate labeled data semantically, but also with physical parameters, quantitative. So we have a new problem. Labeling is not only with names, like oil tanks or ships. We need also to have quantities like the haze of the terrain or biomass. Since now more than 40 years of remote sensing, we have a new product, satellite image time series. Satellites are coming periodically over the same area, observing and generating a movie from space. So this is Bucharest in Romania, observed from 1984 to 2012 with Landsat images. So this is a movie in space which contains very dense information. It's a data cube. It's a data cube in 4 dimensions because we have space, time, and also spectral bands. So complexity of the information is high, and this information is beyond semantics. It's about evolution processes, which are described like evolution maps, but also quantitative classes. So we have now a new category of classification, not only land cover, but evolution of land cover, which is a rising problem in classifiers, methods, but also in semantic, how to name this, how to understand, how to share the knowledge about these evolution patterns. So all these methods need algorithms. And definitely we have in artificial intelligence many methods. I will stop on some of these, but now I want to underline a very particular methodology. It's compression-based pattern recognition. Compression-based pattern recognition, it is mainly based on a distance which is obtained doing only one operation, compressing the images. So we take this example of the database with airplanes, and K, it's actually the length of the compressed file. We take each of these images, we compress it, and we write a number, the length of the compressed file. And we joined them, we compare them. Each of these is compared with all the others, and we take K of xy, which is the length of the joint images compressed file. Just one number. So we have now three numbers: length of the individual complex files and the joint. And this is a similarity matrix. It's very important. It's very important because this applies on a binary data string. It is independent on the sensor and does not require any feature extraction or classification. It's a very objective, directly information the data. The theory, it's emerging from the Kolmogorov complexity theory. And the results are fantastic. We obtain classification, semantic classification, completely unsupervised, grouping natural crossing our data. It's very important because with such method, which is independent on the sensor, on the data, we can deal with the diversity of sensors in space and the diversity of applications. However, remote sensing is more than image. Images are acquired by sensors in space, as Sentinel-1, the Copernicus European program, synthetic aperture radar, but also sensors on ground. So that is a bistatic radar designed at University Polytechnic in Bucharest, where we obtain a satellite SAR image from Sentinel-1, and the microwaves reflected over the city are collected by antennas on the roof of the university, and we obtain a second synthetic aperture radar in a completely different geometry, a bistatic one. The diversity and property of this signal are analyzed with advanced methods like compressive sensing, deep learning, and we obtain a new kind of information. So we have now a kind of sensor networks working together, collaborating, exploiting intelligently the information. So sensor is part of the information processing. We need to understand more than the image, we need to understand the sensing principles. Based on this experience in synthetic aperture radar, we continue and designed systems for precise positioning of satellites in formation flying. So satellites which are flying together, they communicate. And definitely on a satellite is very important to reduce the mass. And we are using existing radio communication between the two satellites to measure their relative position. So this is an example for our antennas in the satellite simulator at the GMV, the satellite company in Spain. So we are using actually remote sensing principles in synthetic aperture radar to design a system for positioning satellites in formation flying. Satellite information, satellite data, needs to be complemented with in situ measurements for many reasons, for calibration, for verification, but also for generating training data set with physical parameters. Thus, we develop sensor networks on ground with application in agriculture. Sensor must have very special properties. They must be very small, very cheap, have a very long lifetime, and use very low power and transmit at very high distance in such a way to monitor large areas. So these sensor networks are a complement in situ measurements, which is very important in Earth observation. All this data coming from different sensors, from different platforms in situ, are analyzed by algorithms, and they should be presented to the final user. Final user end users are coming from different fields: ocean, sea ice, agriculture, forestry, urbanistic. They are in a different type of activity, different expertise. That's why this information must be coded and adapted to the user. Shannon already hinted this. Information transmission should be adapted to the receiver. Receiver are our users. And that's why we design platforms which allow to present results of complex analysis in a simple way. That is Bucharest with a map of displacement, and we can observe millimeter variation of building displacement over the time using permanent scatterers in interferometry. Artificial intelligence and deep learning needs to be specialized for physical parameters, as is the case of parametric SAR data. So opening a new branch of deep learning, physics-aware deep learning, different from computer vision and very specific for Earth observation sensor data. And we need to use visualization. Visualization is very important because we can perceive large volumes of data, analyze, obtain information about native clusters, outliers, type of complexity of the cluster inside, but also visualization are used for testing, understanding methods like deep learning, artificial intelligence, its basic understanding, explainability of the algorithms, and also for debugging complex algorithms. In a resume, in Earth observation, we have large diversity of data, synthetic aperture radar data, multispectral, hyperspectral, time series, so satellite image time series, which are accompanied by metadata text models, in situ, like measurements or photography in situ, and a new kind of data, which are the training and benchmark data, which are accompanied by ontologies and the semantic taxonomies to be shareable information. So dealing with all this information, we need to make a kind of categorization, a taxonomy. And I choose in here a simple representation in three dimensions. One dimension, it is pattern, object, and structure. The other dimension, it is physical parameters. And the third dimension, it is geometrical parameter. So probably most popular sensors are very high resolution, like optical meter, submeter, in which we can observe object. We can recognize an airport, airplanes, ships, or count containers. We have the atmospheric meteorological sensors. They are designed to obtain particular parameters, sometimes very narrow. We can measure the concentration of the ozone, the concentration of pollution gases in the atmosphere. Or we have other category of sensors which are designed to extract a single parameter, a geometrical parameter, the height of the surface of the terrain, digital elevation model, or height of buildings, or displacement like subsidence of millimeters per year. So definitely these sensors, they are not exclusively in spatialized. There are sensors like multispectral or pulsar, which they are both high resolution. We can detect patterns, but they contain physical parameters, and also they can be used to extract geometrical parameters. So this was a very simple taxonomy to position the problems we have in artificial intelligence to go from image recognition close to computer vision to 3D recognition and also to the physical parameter. So at the end, Earth observation is a technological convergence. We have the sensor. We need to understand number of spectral bands, behavior in infrared or microwave, polarimetric or interferometric properties. The sensor, actually, it is mounted on a satellite platform, and we need to understand the mission, orbit, periodicity, sometimes formation flying or constellations. Mission is controlled. We need how the data control is obtained, how the data is transmitted to the ground segment, how the data is processed, how signals from the sensor are transformed in products. These Earth observation products, they are provided to information platform where users can access them and apply methods for ocean color or land cover classification. And the cycle is closed because we learn from existing sensors and we extract requirements and methods for designing new sensors. It's the next generation of most evolved sensors. We learn how to design missions, how to better extract information. So Earth observation is not only image processing. Earth observation, image processing, is actually knowledge requiring sensor, mission, control, ground segment, information platform, and science methods. I go back to the image on infrared. So we have the 13 bands image of Sentinel-1, Sentinel-2, the Copernicus sensor. RGB presents an area of the Black Sea, lakes, a city, Danube, a cloud, and the shadow. The infrared band of this sensor makes a strong contrast of agriculture. Why? Because it's observing vegetation. And infrared, due to diffraction, crosses the cloud. The cloud becomes invisible infrared. However, the shadow of the cloud, which it's characterized by lower temperature, is still visible. So we deal with a physical sensor, a parameter extracting sensor. So it's beyond image processing. We are not limited only to the visual interpretation like RGB, but we go in observation of physical parameters affected by physical principles. And I stop to this example, including also the synthetic aperture radar. So this is a high-resolution Terra-X, the German satellite, synthetic aperture radar. In this image, we observe two image structure. So these are two bright parallel lines, and these are again two bright parallel lines. A computer vision algorithm will decide these are similar structure. They will be grouped together. We have the same area observed by a multispectral sensor. In this, we observe that we have an object of two bright lines parallel, which corresponds to this one, but this one is contradictory. It's only one line, it's a dark one. We take an OpenStreetMap, and that is confirming that is a bridge over the railway. This object is not recorded. These are thematic maps, and not all the objects are recorded or indexed in the map. But we have a picture from this point in this direction, and this object seems to be the power line support of the railway. In Earth observation, we deal with data from multiple sensors. Observation from multiple sensors could be contradictory, so our algorithms should understand contradictory information, but this contradictory information in reality is explained by the physical principles. So having a physical principle behind this information is unified. Sensor combined with other kind of information deals with incomplete data. So thematic maps, they cover some topics, not all objects are indexed. And also we have to fuse information from different modalities like photography, a different geometry, different wavelength. And these are major problems to be solved in Earth observation. So actually what's happening with the synthetic aperture radar? So this double line, actually it is not an object. So one line is a reflection on the power line support, direct reflection. And the second line, it is a double bounce, a reflection on ground and back to the satellite. So synthetic aperture radar is not representing object. Synthetic aperture radar records signature of the object. So we need to learn a physical model to be able to extract the nature of the object. Time series. Satellites are recording now more than 40 years of images over some areas. So in this time series, we have a multitude of information. We observe the extension of the city over 30 years. So city in the 80s was on this area. At the end, in 2012, the city is extending. So there is no highway to the north. So there is a highway to the north. So you observe evolution of urbanistic infrastructure, evolution of vegetation, density of population, important economical factors. As is example, we have an evolution class. So the classes are not a land cover class. The classes are evolution of a natural landscape to an artificial lake. A class is evolution of a construction area in the Parliament House surrounded by parks and boulevards. Evolution is a transformation of a rural area in a residential area. This information is correlated to other information, non-Earth observation, like demographic evolution, and this can be used in application like planning or urbanization. So these are complexity example in satellite image information extraction. So again, in an intermediate conclusion, so Earth observation intelligence deals with a mission intelligence, the sensor intelligence, data intelligence, application, business intelligence. So it's a full chain of the user to data, sensor, mission, and architecture. So again, Earth observation satellite image interpretation, it's actually more, it's the overall mission intelligence with all the aspects. I will summarize now in the last part some particular aspects. Among the most recent results, a very new field which is now developing, the physics-aware artificial intelligence and hybrid methods. I come back to the example of synthetic aperture radar. So there is a lot of variability. We have high resolution or low resolution of the same area. The same area can be observed in a multi-resolution approach. The products can be processed in a different mode, like spatially enhanced or radiometrically enhanced, having full resolution, having less noise. The data can be geocoded, represented in different projections. The same object observed from ascending or from the descending has a different scattering. So we don't need to recognize the scattering, we need to identify the object. The same for incidence angles. The same building has a very different signature at different incidence angles. This is a railway. Due to the steep slope, a loop was designed. Goes down in a tunnel. That is a railway in a SAR image. Goes down in the tunnel. And that is a train. The train is moving. When moving, is changing the reflection. So the frequency of the reflected microwave back to the satellite is affected by the Doppler effect, and the train is focused on a different position. It's clear that learning how to understand this, we need to learn physical models. And the previous example is a double bounce, in which creates a confusion like a doppelganger of the scattering of our data. So this is a concept for physics-aware in synthetic aperture radar. The concept has two components. One component is about explaining the physics of image formation. So synthetic aperture radar actually is very simple. It's obtained by two match filters, one based on the chirp which was transmitted by the signal, as a second one by the chirp which was generated due to the movement of the satellite on the orbit. Echoes are coming back to the satellite with different frequencies due to the Doppler effect. So when taking the spectrum of the synthetic aperture radar, this spectrum can be splitted, and sub-bands of the spectrum are equivalent with antenna looking at different angles. And this is a very basic principle of the synthetic aperture radar, which makes evidence of very particular signature, which are obtained by target scattering in different directions. And the second physical principle in SAR is the parametric signature. So in San Francisco, we have the Market Street. On the left and right side of the Market Street, we have the same kind of buildings, but the signature, the parametric signature is different. It's green and pink. Why? Because the buildings are rotated. So a geometrical factor is changing the signature. And this change of signature could give some confusion with the vegetation. So we need now to understand this physical signature and to embed to encapsulate, to guide our learning process with a physical process. And again, we have one physical process which deals with image formation. That is a design of a basic principle of capturing images in synthetic aperture radar. And the second, it is an interaction of microwaves with land cover or ocean structure. So in here, we went first in using our Bayesian generative model. We use a parametric decomposition, and we extract a basic dictionary, which contains information of pure scatterer, distributed scatterer, surface, volume scattering. And with this basic dictionary, which is meaningful, we enter in the Bayesian inference, and we obtain classes and explanation of the class. So again, woody vegetation or mixed woody vegetation, they are explained by the percentage of multiple scattering, volume scattering, and surface scattering. So you provide classes, a classification, but also a quantitative explanation of the physical process behind. Building on this, we arrive at physics-guided ID. So we have the sensor. The sensor is transmitting microwaves illuminating the scene with a certain polarization, wavelength, incidence angle. Objects which are observed, they are characterized by different material shapes, roughness. Definitely, we have physical models for electromagnetic scattering, but the models are too complex, the scene is too complex. So in here, we propose to use deep learning to go beyond the power of closed model learning, so to learn many parameters, thousands of parameters, which was not possible to be learned until today. The scattering of the microwave object generates a backscattering. That is characterized by double bouncing, single specular backscattering. This is recorded like a single look complex image. Definitely, we can interpret this image like image processing, looking to pixel, texture, or shapes. But these images must be understood, inverted, to obtain land cover, land use objects, and for each of them to extract the type of material, so physical parameters. So this is a paradigm in which we are combining physical models with methods in deep learning, signal processing, in such a way to extract more information compared with the state-of-the-art methods. This is the first example in which we analyze a Fourier spectrum of the synthetic aperture radar, and we extract a tensor in space and frequency. So this space frequency analysis makes evidence of the behavior of the various targets. So different kind of land cover, they have a different representation in time and frequency, which are makes them easy to recognize. Even they are the same type of object, they could have a different signature. But in time frequency, this signature could be identified. Based on this principle, we trained networks using the transformation in time and frequency, and also we learned from polarimetric. And based on this explaining, so guiding the learning with two basic physical principles, scattering and image formation, we arrive to learn signatures which can be obtained classically only if we have a real quad pulsar sensor. Now we can obtain a very similar signature for a single pulsar. So the network is learning basic behavior of the scene and is understanding the signature and generalize it. We can extend this type of learning with semantic. So we have our spectral signatures. We have also the part of the polarimetric signatures, and we complement with a little supervised semantic training of a network. We combine everything in an embedding, and we obtain a new powerful classifier, which is going beyond the classical deep learning, because it's embedding not only the image, but also it's going inside the image, inside the Fourier transform, the physical process, and gives enhanced classification accuracy for almost of the classes. I mean, for all the classes like skyscraper, industrial, or strong scattering, definitely there is not expected to have enhancement for water or agriculture because there is not a particular signature on these areas. And this goes further in generating signatures maps, signatures for canonical parameter extractive on SAR. And that is beyond the classical. Having such explanation, like old double volume mixed, we can explain the type of classes which have been obtained. That is Paris image with GF3 satellite. This goes further in analysis of very complex area, like polar sea ice. So in here we have a classification in water bodies, floating ice, iceberg, glacier, old ice, first ice. However, we don't have only the semantic. We extract, based on the analysis of the SAR signature, an explanation of each of the classes in terms of teardrop reflection, dipole, break surface, double reflection, and anisotropic, etc. So we provide not only semantic, but we provide a physical explanation of how the semantic, how the structure was recognized by the network. I will go very shortly on this slide. These algorithms needs now to be provided to users. And definitely providing a deep learning algorithm to an end user in some application, it's not effective. That's why we need to integrate everything in large platforms. So that's an example of a European project, Candela, in which the algorithms have been integrated to read the data from large archive like Gis in Europe, to interface these archives via an internet layer implementing the Jupyter lab, REST API, and so on, to provide the data to the main applications supported by simple graphical interfaces operated by just few buttons to be understood by everyone, interfaces which are acting on data mining and data fusion algorithms to extract the information. So it's not enough to have only the algorithms. It's necessary to embed these algorithms in information architectures, which to allow easy operation on large volumes of data by experts in other fields, not in artificial intelligence. So using such a system, we succeeded to analyze more than 1 billion square kilometers, having images from US to Japan, from Africa to north of Europe, in such a way to cover large diversity of the data. For this, we extracted almost 100 semantic labels, different type of land cover, and we succeeded to annotate about 12 million of image patches. So these are examples of the power of artificial intelligence in a real application and of the validation results. And I'm going now to the concluding part, in which I will present very, very recent results in an explosive and exciting field, quantum computing applied for satellite images. So presently, quantum computers become more accessible. There are platforms which allows to program on IBM, on Google, or on D-Wave computers. And there is a huge interest to understand the particularities of quantum algorithms and quantum computers, to understand the programming tools and mainly to understand when we can obtain advantages. So there are advantages and how to use this to push ahead the information extraction for Earth observation. And one of the very important things, it is the fact that in quantum computers, the information is physical nature. So the qubit, it's of physical nature, compared with a bit, which is of nature of information in the sense of channel. And these advantages are now exploited. So for example, it's a problem of subset feature selection for hyperspectral images. The problem it is to select the best bands to obtain the best accuracy for certain class in hyperspectral images. So this algorithm was actually implemented using a selection boosted by mutual information and using the QBoost and Kubo like solution for NP-hard optimization problem, which have been programmed on the D-Wave quantum annular computer. So it's needed to extract the statistics for this information in the spectral bands. So measuring the probability and estimating the mutual information. This results in a formulation of a Kubo problem. And this Kubo problem was programmed on both the classical and the D-Wave. And the results have been compared. So we succeeded to obtain an enhancement of the band selection using the Kubo algorithm, which have been programmed on the quantum annular. And also we are using an error correcting output code, again programmed on the D-Wave, to combine the results of various classification with different spectral bands which have been selected. The next result, it is a result on multispectral data. So in here we are using Sentinel data. We are using only the visible channel RGB from Sentinel data. One of the main problems was data embedding. So each of the patch of the image is 64 by 64. However, the input of the quantum, it's only of 16 qubits. This means we need major data reduction. So data reduction was done using a restricted Boltzmann machine, going from 64 to 3 to 4 by 4 by 1. So this was actually implemented on a parametric quantum circuit, which is implementing the classification. And we succeeded to obtain very good results with a major data reduction, demonstrated first on the EUSAT benchmark data set. And later we went on an actual satellite image, Sentinel-2 of Berlin, where we obtained classification of urban and the vegetation area. So we succeeded to extend and to demonstrate the quantum advantage quantum methods for different kinds of data, multispectral and hyperspectral data, for two problems, the problem of classification and the problem of band selection. And the last example from today's presentation, it is the natural embedding of stock parameters on a parametric synthetic aperture radar in a gate-based quantum computer. So here we go directly straight to the physical principle. So I come back to the example of San Francisco Market Street. So buildings on the left and right side of the street, they are identical in nature. However, the signature is very different. It's different because the building orientation on one side, from the other side of the street, the orientation is different. this is orientation, and this is the orientation here. So this change of orientation, it's changing the signature. And definitely that could explain the nature. And since qubit has a physical nature, we approach the problem by projecting the Poincare polarimetric representation on the qubit. So we have a mapping of the physical information directly in the quantum format. And using this mapping, we designed the quantum classifier in such a way to treat directly the states which are related to the single bounce, double bounce, or volume scattering. And these physical processes are mapped in the quantum states. So these are examples on the architecture of the quantum gate which was implemented. These are examples on the extracted Jones parameter and how they project on the qubit in the classifier, and the final results of classification, which is now explainable algorithm implementing on a quantum computer. And arriving at conclusion, so we propose now a new methodology for Earth observation sensors. This methodology actually is broader because that refers actually to the category of sensor, which could be medical, astronomical, astrophysics. So we are developing these physics-guided IE methods for sensor data which are extracting physical parameters. Earth observation is one of the cases, and is different for photography, which has different challenges in interpretation. And definitely this embeds advanced statistics and signal processing and complex image analysis. That relies on electromagnetic modeling in this problem. Smart sensing and computational imaging, we have to know how the image formation takes place, the physics behind. We need to develop artificial intelligence for radar, physics-based and aware methods, and definitely this makes a transition to quantum. And topics which are now under very much actuality are the prediction and causality, and definitely implementation hybrid, explainable, trustworthy, and reproducible in such a way that we can transfer this in practical applications. So I thank you for your attention, and I conclude at this point.
Thank you very much, Dr. Mihai, and it was indeed a wonderful presentation and very informative lecture. And a few things really are eye-opening, like the cube boost classifier and the quantum binary classifier, and the insights from the physics-guided AI for Earth observation systems. I was there are a few questions in chat, but I had a query if the time permits me to ask for. My question is that when we talk about physics-guided AI methods, if we want to apply it for mineralogy, like what type of physical models should be taken into considerations?
I apologize. Could it be possible to repeat the last part of the question?
Yeah. If I want to apply the physics-guided AI for obtaining the mineralogy of surface of the planet using the deep learning approaches, like what type of physical models should be appropriate for that?
Yes, no, it's very similar to the problem of Earth, and in principle so the question refers to planetary observation, yes? Yes, for planetary observation, the problem is getting a little bit simpler compared to the Earth because of the lack of vegetation. However, the planetary problem, I want to tell that I do not have too much experience. I was involved only in a Mars mission. So For planetaries, the challenge is, simplification is because of the lack of vegetation. So land cover can be observed directly. Atmospheric effects, they could be absent or very much reduced because atmospheric effects on planets sometimes can be reduced. Okay, if there are planets like Venus, atmospheric effects are very strong, and again, it's coming to synthetic aperture radar observation. The challenges are actually by the lack of information of reference data. So on Earth, even in the polar area, we have some reference data, some measurements. And actually, in this point, the qualification of the uncertainty, the trustworthy aspect of the information, i.e., becomes crucial because the algorithm could provide a degree of probability of trust in the results. And this must be objective with very few physical models knowledge on the ground, on the planet truth, and with many uncertainty on the physical models. And these are really interesting challenges.
Yeah, thank you so much. I would like to take a few questions from chat, from our participants. The first question is that is it possible to process phase information also in DL for PS INSAR?
Yes, for sure. So this is a perspective of these methods to go deeper in interferometry, both for artificial intelligence and for the quantum. In terms of quantum, we developed algorithms for residue connection in viscous flow for phase unwrapping. And definitely analysis of permanent scatter is a very important topic, and artificial intelligence can benefit a lot to this, mainly for trying to find displacements which are in various directions, understand patterns of deformation which could be observed.
The next question is, what band of Sentinel-2 is used for DL?
Sentinel-2, it's a sensor operated in a C-band at 5 centimeter and has two polarization. Resolution of a single complex is 20 meter to 5 meters. And the standard ground length products are 20 by 20 meter. And there is a high resolution mode, which is used only for small islands over the ocean, which goes in resolution better than 5 meters, sometimes 1 or 2 meters. All the Sentinel data is available free and open via the European Space portal, SHIHub. So if someone needs information, can find it directly on ESA, or can send an email, I can provide the information. So all the Sentinel data, Sentinel-1, synthetic aperture radar, Sentinel-2, multispectral, 10 to 20 meter resolution, Sentinel-3, and Precursor, all this data, it's free and open.
Yes. And looking at the time limitations, we can take one more question. Like, how much scope is for impervious surfaces, especially like road extraction from high resolution satellite images?
So there are already teams which developed such algorithms. The road extraction is mainly done using very high resolution satellite submeter and airborne observation for precision. And there are groups in Europe, also US, which are working intensively, and there are already companies which are using these algorithms. So one of the most methods have been developed by Julia Tarabalka in France, in Sophia Antipolis.
Yeah, and it's very kind of you to take the questions, Professor Mihai. And there are a few comments in the chat from the participants thanking you for the excellent and informative session. It's really appreciable. Thank you so much.
No, thank you. Thank you for the invitation. I'll be glad to remain in contact, and anyone is have a question could contact me. Thank you again. And
as a token of our appreciation, we would like to present a e-memento to Professor Mihai. I would request Tejal to present it. So, and we just wish that the next time we all meet in person, away from all these e-platforms and presenting the mementos.
yeah, that would be great. As always, very much. Once again, thank you very much.
Thank you, Professor Mihai. I would request all the participants to put on their cameras so that we can have a group photograph. Thank you so much.
Once again, thank you very much, and I tell you goodbye and hope till soon.
Thank you, Professor Mihai. Good day.
Goodbye. Goodbye.
This brings us to end of very informative sessions on Geo AI and physics guided AI. I would now carry forward for the panel discussions. So over to the organization team. Thank you so much, and thank you for providing me the opportunity for chairing the informative session. Thank you all.
ఇది ఎక్కడ అది పక్కన సింగర్ వీడియోస్ చేస్తారా రేపు టెస్టింగ్ ఆర్ఎస్ చెప్పండి మీరు రెజిస్టర్ అని చెప్పి చేయలేదు
Okay, good evening, everybody, and welcome to the panel, the very last session of the very last day, which is always a bit of a challenge, but thank you. Yes, Chirag, would you want to first of all go and mention this, and then we get started?
No, sir, you can start, sir.
Okay. So first of all, a very warm welcome to my good friends and panelists. I have Devdut with me and I have Nirmal with me.
Hi, Amit.
Hey, lovely to see you guys. Old friends of mine. One is new friend, another is an old friend. So let me first introduce them to you. My friend Devdut, we were together in IBM Research, and he used to work in software engineering, and then we worked on some stuff to do with data together. And since then, my God, he has been busy. He then went to Mintra, and then he went to Hike, and now he's at ShareChat. And he's been, he's got his hands dirty with a number of technologies, computer vision, modeling, recommender systems, you name it. Okay? And so it's lovely to, and we only exchange jokes on WhatsApp platforms. It's good to see you, face to face and actually have, something of a semi-technical discussion. So thanks.